Alright, so we're gonna keep going with more integration techniques today, doing some new stuff, namely partial fraction decomposition. So our objectives won't make sense just yet, but we're gonna determine partial fractions of a rational function and then integrate them. So I'm gonna start with this. If I wanted to solve this, this sum, what would I do? Not a trick question, but what would my first step be?
Like you.
If I want to add these two fractions together, what's my first step?
Find the common denominator.
Okay,
We could multiply one or something.
okay, you're right. I've got Zoom and Skype speaking at the same time. It's a little hard to hear on my end, but you're both right. So multiply the left by the right, or get a common denominator. So to get a common denominator, I'm going to multiply this left one by x plus 2, this right one by x minus 3. Once I've got a common denominator, we can add straight across and combine the like terms. Okay, what I want to do is I want to be able to work backwards. So I want to be able to get from our answer here, after we had added these two fractions together, into the original two fractions that we were adding together. And the reason why I want to work backwards is because if I was going to try to integrate this function, if I was going to integrate 7x plus 16 over x squared minus x minus 6, then I would say my u would be the bottom part of this fraction, x squared minus x minus 6, that makes u prime 2x minus 1, which I can't rewrite in order to become 7x plus 16. Even if I multiply by 7 over 2, in order to make this 2x 7x, that'll still leave me with a negative 7 over 2, which is not 16. But if I can break this apart into the original two fractions, then we will be able to integrate. Okay, so here's how we do it. The first thing we're going to do is we're going to start with our large fraction that we can't integrate, and I'm going to factor the denominator. So if I factor this bottom part, zoom in here. Okay, if we factor the bottom part of this fraction, I'll get x times x plus 1. Then I can break this apart. So I can assume that there is some number over x plus 1 plus some number over x, that when I add them together, it could give me this fraction. In order to add them together, I would have to get a common denominator, so I'm going to cross multiply. A times x would be on the left side, and then b times x plus 1 would be on the right side. And that leaves me with, if I add all of the numerators together, I should get what's on the left side. So that leaves me with an equation that we can use to solve for a and b. If I factor out x here, then I've got a plus b equals 3x plus 1. And we can combine our common denominators to create a system of equations. So a plus b must equal 3, and b must equal 1. If b is 1 and a plus b is 3, then a must equal 2. And we can split this back up into partial fractions. Okay, again, the reason why we want to do that is because that will allow us to integrate. So now I could say the integral of 3x plus 1 over x squared plus x is the same thing as the integral of 2 over x plus 1 plus 1 over x. Which is great for us because if I set u equal to x plus 1, u prime will be dx, which is what I have on top, 1. So I can factor this out. This will be 2 and 1 over u. So that's u prime over u, plus the integral of 1 over x, if I split this apart, would give me 2 times the natural log of u plus the natural log of x plus c, or 2 times the natural log of x plus 1 plus ln x plus c. Okay, any questions on what we did here? Okay. So I'm stealing this from Hull University, but there are 4 different types of these partial fractions that we can do. So the first type, what we just saw, is when you have linear factors in the bottom, and we solved them the same way that we just did in the previous slide. Linear factors means my largest power of each factor is x to the first power. And if we do, then we can split this up into parts of a fraction that would be a constant over my first factor and a constant over my second factor. Okay, for type 2 is whenever we have higher order factors. So something like this. If I have x squared, I'm not a linear factor anymore. So every time I have a higher order factor, there is a possible term that is every power less than that higher order. So if I broke this apart, this would be 3x plus 1 over x minus 1 times x squared plus 1 could be equal to some number a over x minus 1 plus bx to the first power plus c over x squared plus 1. So I have an extra term in this last fraction for every 1 power less than my largest factor. So if this had been x cubed plus 1, then I would have bx squared plus cx plus d. If it had been x to the 7th power, I would have a constant times x to the 6th, a constant times x to the 5th, a constant times x to the 4th, a constant times x to the 3rd, all the way down to just a constant times x to the 0 power. Okay, then for repeated factors, or our type 3, where we have x minus 1 squared, so we're doing x minus 1 twice. And the repeated factors need to be checked for a solution for each possible power. So what that means is something like this. 36 over x minus 1 squared times x plus 5 could be broken apart into actually, I can split this up just like this. When I go to get a common denominator, I won't multiply this a by an x minus 1. So this will give me the term that I need that's only multiplied by x plus 5. So that gives me an x and a constant term. But this term here for b, I would have to multiply by another x minus 1 and an x plus 5. So that actually gives me a constant x squared term as well. Anytime we have repeated factors, I'll have to do a separate constant over every power all the way down to 0. So this is x minus 1 squared and x minus 1 to the first power. Both have to be tested for different constants. And after that, everything else is the same. Okay, I'm going to work all 3 of these out in a minute, but for the last one, anytime you have an improper fraction, so that's a fraction where your largest power on the top, so in the numerator, is larger than your largest power on bottom in the denominator. In this case, my largest power on bottom is x cubed, my largest power on top is x to the 4th. Then I'll need to use some sort of polynomial division in order to simplify the fraction before we can start. So either synthetic division or long division. Okay, any questions on the different types? Okay, I'm going to give one example of each. Okay, so starting with type 1,
Oh wait, I'm a little bit confused. What's the difference between type 1 and type 2?
Higher order factors. So for type 2, this is not a linear factor. This is a quadratic factor.
Oh, okay.
Um, Type 2 could be any higher order though. So it could be a cubic, it could be a quartic, it could be a quintic. So any type of power that is not 1 in your factors. Okay, good question. So over to type 1. This is a type 1 because each factor is linear. And that means we can just throw each part as the bottom of our fractions and use a constant. So this is some constant over x minus 1 plus some constant over 2x plus 1 should be able to equal this larger fraction. So I'm going to cross multiply. And we'll solve for a and b. Okay, so I've cross multiplied. This is a times 2x plus 1 and b times x minus 1 gives me the numerators. I can set those numerators equal to the top to solve for a and b. And now I'm going to do this slightly differently than what they have on the slide, but you can pick any values for x that you want in order to make this true. So I'm going to pick values for x that will cancel out either a or b. For instance, if you say, I guess this is what I already had on the slide, but x is equal to 1. And then at x equals 1, this term will become 1 minus 1 is 0. So I'm going to end up with 4 equals 3a plus 0 times b, or 3a equals 4. Therefore, a is 4/3. Okay, I could also plug in x equals negative 1/2, because that would make this
Wait, where did the 4 come from?
3x plus 1. If x is 1, that's 3 times 1 plus 1 is 4.
Are we assuming the number to be 1?
Yes, you can pick any value for x for this equation that you want, and it will still be true. So
Okay.
I picked 1 because that would
Wait,
make my b's
Mr.
cancel.
Brennan, but where did the 4 come from?
This is 3x plus 1 on the left side. So this would be 3 times 1 plus 1
Oh, okay.
gives me 4.
Okay.
Okay, so I chose x equals 1 because that makes my b's cancel. If I want to make my a's cancel, I could choose negative 1/2. So this would become 2 times negative 1/2 plus 1 is 0. And then I would multiply that by a to get rid of my a's. Okay, so I'm going to do that really quick. So for our second one, if x is negative 1/2, and then this will become 3 times negative 1/2 plus 1 is equal to a times 0, we said. So 2 times negative 1/2 is negative 1, plus 1 is 0. Plus b times negative 1/2 minus 1. Okay, if we simplify, this is negative 3/2 plus 2/2 equals negative 3/2 times b. Or negative 1/2 equals negative 3/2b. So if I multiply by 2 and divide by negative 3, I'll get b is equal to 1/3. Okay, any questions on this one? Okay, so what I'm going to do with that, here I have an a. I'm going to substitute as 4/3. This is 4/3 times 1 over x minus 1 is 4 over 3 times x minus 1. Okay, and then I've got my b, which we said is 1/3. So I'm going to plug that in. That's 1/3 times 1 over 2x plus 1 is 1 over 3 times 2x plus 1. And we have our partial fractions on this side. Okay, any questions on what we did here? Okay. For a type 2, so this is any time that we don't have a linear factor. In this case, this x squared plus 1 is not linear, it's quadratic. So that means instead of just having a constant over the x squared plus 1, I'm going to need to have a constant for an x to the first power term as well. Okay, so now when I get a common denominator, this will be a times x squared plus 1 and bx plus c times x minus 1, which gives me this step. So our general equation for the numerators, on the left side I've got 3x plus 1, on the right side I've got a times my bottom of the other one, which is x squared plus 1, plus bx plus c times my bottom of the left one, which is x minus 1. Again, we can plug in any numbers we want to solve for a, b, c. So I'm going to start by plugging in x equals 1, since that will make this term equal to 0. When x equals 1, I could say this would be 3x plus 1, so that's 3 times 1 plus 1 is 4, equals a times 1 plus 1, plus bx plus c, so that's b plus c times 0. Or a is equal to 2. Okay, I'm going to do something a little bit weird for this next one, but if I actually multiply this... Yes?
How did 2 came out? Is it also like assumption?
Again, we said we plugged in x equals 1. So if I do, this is x squared plus 1. So that's 1 squared plus 1 is 1 plus 1 is 2.
Also, if we are doing this one, we always put the x as 1.
And the reason why I chose x equals 1 is because of this term. If x is 1 right now, then I don't have any b's or c's, right? Which will let me solve for a. You can pick any x you want, but you'll try to pick x's that let you cancel other constants. That way you can solve for the constants.
Okay, thank you.
No problem. So it's a bit like a puzzle. You can solve it using a system of equations, but if you don't want to do that, you can plug in any x values you want, and it'll work that way too, which is what I'm doing. Okay, for this next one, I'm going to use a different technique. So I'm going to take a look at my coefficients of x squared. So what I mean by that is, if I multiply this out, this will be ax squared for my right side. This is my only x squared term from here. And on this side, my only x squared term would be bx squared plus ax squared plus bx squared. And then we don't have any x squareds on the right, because all of my coefficients of the same power have to equal each other. I have to be able to combine like terms. I could say that a plus b, if I factor out this x squared, must equal 0. And if that's true, since we know a is 2, then b must equal negative 2. Okay, so for that one, I just multiplied out the terms that would give me an x squared, since that way I don't have to worry about c. And that gave me an equation that I could use to solve for b, since we already knew a. I'm going to do the same idea for c. So for c, I'm just going to look at the constants. Again, on the left side, my only constant is 1. For my a term here, after I multiply this through, my constant will be a to the first. So that's a times 1. And for this binomial, if I FOIL, this will be bx squared minus b plus c minus plus cx minus c. So my only constant here is minus c. So that gives us an equation. If I just look at the constants, which have to equal each other, 1 must equal a minus c. We know a is 2, so that lets us solve for c. So therefore, c is equal to 1. Okay, then I can substitute back in. Anytime I see an a, replace it with 2. Anytime I see a b, replace it with -2. Anytime I see a c, replace it with 1. Okay, that gives us our partial fractions, which I could then integrate from there. Any questions on what we did? Okay. And type 3 is anytime you have a repeated factor. So here I've got x minus 1 squared. That's a linear repeated factor, is my type 3 marker. So that just means instead of testing some constant over x minus 1 squared and calling it a day, I'm going to have to test for both x minus 1 to the second power and x minus 1 to the first power. That's every power less than the power that we repeated. Because when we start cross-multiplying to get my common denominator, that will give me a term x to the first power and a term x to the second power when we multiply this out. If I do, this first term, to get a common denominator, only needs to be multiplied by x plus 5. So that gives me a times x plus 5 for the top of my first one. The second term, though, needs to be multiplied by both an x minus 1 and an x plus 5 in order to get my common denominator. So that gives us our middle term of b times x plus 5 and x minus 1. And our last term, c, would need to be multiplied by x minus 1 squared. Okay, that would give us a common denominator of